light story. Okay, so the last talk of the session, end of our meeting, will be given by Jeongwan Haah from Microsoft, and he'll talk about quantum cellular automata in 3 dimensions.
Yeah. Thanks for giving me the opportunity. Do I have mic? Oh. So this is another work with Lukash and Matt. This is also a result of resolving one subtlety and that arises in the topological phase. But before I get into that aspect, let me just give you what the object we are studying. So the name is QCA, but I think it's better not to de-abbreviate that acronym because it's not too instructive. So let me keep that acronym as it is. So let me use this word as it. And this is just the So it is just the locality-preserving automorphism of algebra operators on lattices. So for those who are not familiar with the word automorphism, morphism means that you always preserve certain algebraic structure. So if you have a group, then you have to preserve the multiplication rule at the domain, at the codomain. Auto means that it maps from itself, from something to itself, and is invertible. And since we are talking about algebra, the conditions, I will use Greek letters for generic QCA. And the conditions are identity should be mapped to identity. And so every product should decompose, but the complex coefficient should be pulled out for all choice of L, A, B, and those things. So this is my definition for automorphism. And the inverse exists. Locality preserving means that what you expect. In a lattice, you give me an operator that acts on some site or some collection of sites. And then the mapped image of that operator should reside, say this point was S, then the image of that operator should be supported around that given site. So just to avoid the confusion, this rules out rotation if you're working on the flat space, for example, because in rotation you have to pick a rotation center. And the operator around that center is, well, it remains there, but operator far away is moved very far away. So rotation is ruled out, but translation is included. So what kind of questions can you ask about this? The one typical example, when you know nothing, we start with an example. One example is, of course, just a local unitary. Although I am given with a large lattice, I can start with some unitary that acts on two sites, say, and then given any operator, I can conjugate by that unitary. Obviously, that preserves locality, and any finite composition of those should also preserve locality. And you can apply those unitaries if they are not spatially overlapping, and that gives rise to the notion of quantum circuit. So the quantum circuit is a natural consequence of considering this locality preserving automorphism, starting with just a simple two-site unitary. There is a non-trivial examples, meaning that automorphism that is not realized as a quantum circuit. Very mundane example is a translation. Just to entertain you, consider a fermionic chain where you have two real Majorana modes per site. typical, you can write down a trivial Hamiltonian for this one. But you can also think about automorphism that translates one Majorana mode to the next neighbor. Well, obviously it preserves locality. I just shifted one unit. It didn't go far away. But we know that if you start with the trivial fermionic chain, then the mapping will give a state that is Majorana chain, which is non-trivial. And we know that that transformation should not be obtained by local quantum circuit. So mundane translation is a non-trivial example. And it has been the only example for the last 10 years or so. So there was a paper by Gross, Nesme, Fox, and Werner. They consider not the fermionic version, but just a mundane spin version with a strict locality. And they classified completely such a QCA. The only possibility is just a quantum circuit followed by some shift. That's all.
Excuse me.
Yeah.
So this degree freedom per site is integer or just a non-zero mode in this translation example?
Oh, in this example, so I was considering just the operator algebra. So,
I see.
so say this is 2k gamma 2k plus 1. And every even mode is mapped to odd mode and odd mode to map.
Excuse me. Is the discussion here, do we focus on the state of vector in the Hilbert space, or do we consider the operator in the Hamiltonian sense for this
I primarily consider the full operator algebra,
the operator, not the state?
not just the state. So having understood something means that we can think of them as trivial to a large extent. So let's consider translation and quantum circuit as trivial QCAs. What else? And that's a natural question. And that has been open for a while. And then from end of last year towards this year, we make some progress. And that's the topic of this talk. So let me briefly write down the results. So it turns out that any QCA living on the 2 dimensions is also trivial. So you can find the quantum circuit followed by some translation. In this case, the translation can be along 2 directions. This is by Friedman. And this is for spins. We do not have an answer for fermionic systems. Actually, this paper does not address fermion, so fermion is maybe you may consider this open too. 3D, we do not know, but what I can say, assuming very strong, very plausible conjecture, this is at least non-trivial. And let me give you an example of this. And 4D and beyond, we have completely no idea.
So you mean at the moment there's no explicit construction, but there's some evidence that it's there.
I'll get to that. The construction is explicit, but the non-trivial is this part.
Excuse me. Do you consider generic space group?
Space group, no. Like I said, no, the rotation is excluded from the onset. So let me start with a little bit of entertainment for you. Projector. So following Xiaogang's question, let me show you the explicit QCA. Although, when you see it, you will immediately say that, oh, I don't want to see that. Here's the reason. So the particular QCA is started with this Hamiltonian. This is adopted from the paper from 2013 by Brunel, Chen, and Witkowski and Jeongwan Haah. It is proposed to be a beyond cohomology SPT under time reversal. It is an instance of so-called Walker-Wang model, where we construct a three-dimensional lattice Hamiltonian with an input of some tensor category. It can either be modular or not modular, but in this case it is modular, and the input in this case is a three-Fermion theory. There are two spins per link, and there are like loop constraining terms and some fluctuation terms. That's all. The ground state is unique. There's no topological charges. And this is exactly solvable model. For the last 6 years or so, it is proposed to be symmetry protected trivial state, I'm quoting Jeongwan's language, but no one has wrote down the actual disentangling circuit. The only evidence was that the ground state was non-degenerate. And we found a disentangling transformation by an explicit calculation as shown in this mathematical script. And these polynomials describes one particular alpha. It is 12 by 12 matrix, whose determinant is 1. This is not exactly the operator algebra that you encounter, but some abstract representation of it. And it preserves all the commutation relation. And it's described in terms of finite long polynomials, so it preserves locality manifestly. So,
but how the 12 by 12 matrix act on the operators, or whether there's some?
That is a bit of digression, which is not too important, but each row describes the image of one particular Pauli-like matrix.
Oh, I see.
Yeah. It may look complicated, but it's just 10 by 10 by 10. So an operator at a site is mapped to an operator that is supported on box of size, linear size 10. So the weight of that operator is at most 1,000, a constant. So why is that QCA interesting? So, apparently I will not write down that QCA again. So, as it is routine in this field of topological phases, we should consider surfaces. The Hamiltonian I showed you is defined on the bulk in a translation invariant manner, and we know that I claim that my transformation maps the ground state of this Hamiltonian manifestly into the product state. So if my QCA, the huge matrix I showed you, was a composition of local quantum circuits, then one very important feature of a quantum circuit is that you can drop the gates. If you remember the diagram, my circles are gates. It is extended on the lattice like that, but I can always erase them. And I can choose to not apply them. That's my arbitrary choice. Nothing prevents me from doing that. Now suppose I introduce some vertical coordinate, and I apply my disentangling unitary only in the deep bulk, my hypothetical quantum circuit that realizes the QCA I described. Then I can always terminate it like that. Deep in the bulk, this is by definition disentangling the Hamiltonian in a manifest way. So the new Hamiltonian conjugated by this quantum circuit, is manifestly fixing each qubit to, say, spin up. Here, I did not do anything, so it preserves the original Hamiltonian, which admits, this is important fact I missed. The Walker-Wang model that I adopted from the 2013 paper, you can define the surface Hamiltonian in such a way that the annealing excitation behaves like a free fermion modular tensor category theory. This theory is whose fusion rule is the same as the toric code, but they are all fermion. There's no boson. So in particular, it is the chiral theory. So coming back to the bulk and considering this hypothetical quantum circuit, I could disentangle deep bulk without touching anything at the boundary. And the disentangled bulk has a manifest trivial Hamiltonian. So it is up to me to drop this system entirely. It is very important that my QCA disentangles this Hamiltonian manifestly. It disentangles all the spectrum, all the energizing states to the product state. So I could terminate this system after some distance order of 1. Then what I get is strictly two-dimensional theory that realizes 3 fermion. There's no trouble with that so far. However, this is an automorphism. It preserves all the commutation relation, and I started with the commuting Hamiltonian. So conclusion is, if my disentangling unitary that manifestly disentangles the whole spectrum of the 3 fermion Walker-Wang model, if that was a circuit, then I obtain a two-dimensional commuting Hamiltonian that realizes 3 fermion theory, which is chiral. And that is not believed to be possible. So that's the non-triviality argument. And this is the step we do not have a proof, whether commuting Hamiltonian may realize such a theory in 2 dimensions.
Sorry. Is it obvious that another copy of 3 fermion can't show up on the other boundary when you cut?
So, okay, right. You pointed out the very important aspect. It is, well, I think I'm saying it twice. It is important that the disentangling QCA does the job manifestly, meaning it maps each Hamiltonian term to the sigma z, no more. So I can certainly truncate my system without introducing any non-trivial boundary. So having said that there is a non-trivial QCA exists, let me give you some idea of the calculus of QCAs.
So just on this lower boundary, whether because your map is not side by side, so there's some fastness. So this lower boundary, whether
Here?
the lower boundary,
Here?
yeah, this one, yeah,
Yeah.
can have something. Yeah.
No. So okay.
Yeah, the things are maybe lower boundary non-trivial is you give the 3 fermion.
Okay, so this is an important point. So let me spend my remaining time to clear up that part, ignoring all the rest. Yeah, this is important. So I actually glossed over one detail. My Hamiltonian was like, well, it's a bit pain to write down all the terms, but it had a 6 sites per unit cell. And if you remember the diagram, there are exactly 8 Hamiltonian terms per unit cell. Well, it is mismatching. If the every word I said was true, then the image of this Zi should be the Hamiltonian, but which is not the case here. But what we found is that you can always choose a different Hamiltonian with the same ground state, same entanglement structure over all spectrum in such a way that there are exactly 6 terms. And they define the same ground state. And using this Hamiltonian, now using the commutativity, let's do this. Let's say, let me denote these original terms as unprimed and newly found ones by primes. And define the original Hamiltonian before applying this hypothetical circuit, HP, and slightly overlapping region, but HP prime. In the middle, there are redundancy. There are huge redundancy, but it doesn't matter because they're all commuting. There's no trouble. The ground state is okay so far. And then I introduce the 3 fermion surface Hamiltonian, as was originally proposed. So up until this point, nothing has been changed from the 2013 paper. This overlapping region is somewhat new, but I don't really care. Below, the original terms are forgotten, and I replace them with the new terms. But again, ground state is the same as before. Now I apply truncated QCA, which is hypothetically realized by a quantum circuit, like where the transition region is confined to this slab. Here, H prime P is going to be manifestly mapped to Zi, trivial. Up there, nothing will be changed. In the middle, something crazy happens, but we don't have to worry about that. Then I truncate this portion after applying my hypothetical circuit. So it is very important that there exists such a new Hamiltonian that realizes the same ground state.
Question.
Yeah.
So since there's the notion of locality on the site, can you evaluate the dimensional Hilbert space on the upper layer of the 3 fermion and also the dimension of the Hilbert space on the lower layers? I wonder whether the dimensional Hilbert space on the lower layer per site will be larger.
No.
Larger.
So it is attempting to count that, but it's a tricky problem because you, anyway, formally started with the infinite dimensional Hilbert space.
But evaluate per site.
Evaluate per site. Still, you have a free space that goes up. There's no proper notion of per site Hilbert space.
On the upper layer and on the bottom layer, let's say.
They do not cancel. They just add up. So let me advertise one more result without using, well, actually, it goes with a similar procedure. It's not only non-zero, but actually, so this was a result up until end of last year. This is a new piece. So the group of all QCAs in 3 dimensions is not only non-trivial, but actually contains infinite generators, assuming one conjecture that a commuting Hamiltonian in strict two dimensions can only realize quantum double of something.
What is P?
P is a local Hilbert dimension that is chosen to be prime.
So 2 for Z2 cubic.
So here P can be 5. Here P can be 3. So it's a local Hilbert space dimension. So I shouldn't write more, but just in words, these were constructed in a similar fashion, adopting Chong and Sentil's construction of coupled layer and condensing bosons, leaving out certain non-double models at the surface, starting with copies of toric code. And I have for the remaining time, let me ask a math question, very well formulated, but I couldn't find any reference. So it's related, but the explaining connection will take me like 10 more minutes. So.
But actually, we're out of time though.
Oh, okay.
Well, let's thank him first.
Yeah, good question.
Thank you. So there's a weak theory, very well developed over fields. It is a study of symmetric forms that are non-degenerate over fields, and the equivalence relation is given by congruence transformation. So then I declare that there are equivalents if for any invertible matrix E. Under this equivalence relation, you can classify these objects. It's called the weak group.
Stability.
Sorry?
You're allowed to stabilize also.
Yeah, but over rings, and in my case, there are two versions, but the simpler version is these symmetric forms that are anti-Hermitian over the ring that is filled with, over a Laurent polynomial ring, where the involution of the ring is given by the inversion of variables. In that setting, what's the weak group? That's my question.
So now we should ask the audience if there are any answers.
I call a friend.
Yeah, please. So it naturally, there is a homomorphism from this group of QCAs into this group. That's why I'm asking this. Yeah.
Do you think all Walker-Wang models will be disentangleable by QCA?
I would believe so, but calculation becomes too complicated, and it is apparent that we need a new tool.
Max?
Is the semion part of this?
No, actually, these groups are precisely the weak group of the finite fields of Fp. Yeah, the double semion does not appear here.
Single. There is a Walker-Wang model based on the semion category.
Yes.
One
Yeah.
So that's not part of it.
No, that's not included. Maybe that example will add up another factor here. Sorry? I think Dominic has that.
You mentioned this question of whether the Walker-Wang model can be disentangled by what you would call trivial QC, but quantum circuits. But is that question still open?
Yeah, right. So, this is the connection to the classification of topological phases, let alone the resemblance in question. One subtlety is that the Walker-Wang model with the three fermion theory is supposed to be SB trivial. But we do not have a disentangling circuit, but we only have disentangling QCA that is shown to be non-trivial. So, is there a invertible state in 3 dimensions? The existing classification proposals do not admit one. but this one shows that there's a tension. So that's an open question.
Okay, why don't we thank Jeongwan again? And I think Ashwin wanted to make some remarks to wrap up the meeting.
Yes,